5 days ago, this channel told you NASA was sending 4 astronauts into the most active solar cycle in 2 decades. We told you the window was open. Yesterday, the Sun answered. An M7.5 solar flare, 1 decimal place from X-class, erupted from a sunspot aimed directly at the Artemis II crew. It arrived at the spacecraft in 8 minutes. The shelter takes an hour to deploy. The crew couldn't react before the radiation passed through them. And here's what nobody is telling you. That sunspot has a 15% chance of firing something bigger in the next 72 hours. The crew reaches maximum distance from Earth tomorrow. They cannot come home early, and what the Sun is capable of when it truly loses control makes that M7.5 look like a whisper. Before we begin, if you genuinely enjoy what I do here on Project Nightwatch, make sure to hit like and subscribe so you don't miss a single update as this story unfolds. Drop a comment with where you're tuning in from, what time it is there, and whether you think NASA should have delayed this launch. Now, let's get into it. Part 1. The problem with impulsive flares. On April 4th at 1:17 in the morning Coordinated Universal Time, the Sun did something that nobody on the ground saw coming, and the 4 people who needed to know found out by instrument readings alone. Commander Reed Wiseman, pilot Victor Glover, mission specialists Christina Koch and Jeremy Hansen were 4 days into what was supposed to be humanity's triumphant return to the Moon, strapped into the Orion multi-purpose crew vehicle, somewhere out past the point where the Earth starts to look small. 169,000 miles from home. That distance is significant. That distance means they were beyond the magnetosphere, beyond the Van Allen belts, in a place where the only thing standing between them and the raw output of the Sun was the aluminum hull of their spacecraft and whatever they could improvise in the next few minutes. The flare that lit off that morning was an M7.5. On the logarithmic scale that measures solar flares, that puts it about 75% of the way toward an X-class event. To put actual numbers on it, an X1.0 flare is exactly 1.33 times more energetic than an M7.5. Not 3 times, not 10 times, 1.33. That small margin might as well be the distance between a routine mission and the kind of event that ends in a plaque on a memorial. This is the mathematics of the solar maximum, and it is brutal in its precision. The thing about the M7.5 and the 3 other significant flares that Region 4409 fired off that same day is that they were all impulsive. All of them. No coronal mass ejections, no slow build-up of plasma lifting off the solar surface, no hours of warning from the radio pulsations that accompany the typical major flare. Just pure energy, released in a confined burst, converted into electromagnetic radiation and a shower of particles moving at a significant fraction of light speed. The radiation itself travels at light speed, 8 minutes and 20 seconds from the Sun to wherever the crew happened to be in that moment. The fastest energetic solar particles arrive anywhere from 15 to 30 minutes after the flare begins. The Orion storm shelter, if they had somehow deployed it instantly at the moment the GOES satellites detected the initial radiation burst, takes up to 1 hour to assemble. The Astrorad radiation vest, which provides some additional protection to the critical organs, takes somewhere between 5 and 10 minutes to put on, assuming everybody is awake and ready and nobody is panicking. The HERA instrument aboard Orion detected the radiation as it arrived, as it was arriving. By definition, once an instrument detects radiation, that radiation is already passing through the crew. There is no warning, there is no time, there is only the event and then the consequences. This is the fundamental problem that nobody really grasped until the crew was actually out there, past the point of return, watching the sensors spike in real time. The shelter protocol, the entire architecture of radiation protection for the Artemis program, was designed for a completely different threat model. It was designed for the kind of event that gives you hours to prepare. It was designed for CME events, for the slow build-up of particles that pile up at Earth's magnetosphere like traffic at a border crossing. Nobody designed it for a flare that moves at the speed of light, because nobody had ever had to. The impulsive flare is the kind of threat that exists in a category by itself, and until April 4th, it had always been a theoretical concern rather than something actual human beings had to sit with while travelling to the Moon. Region 4409 is an EAI magnetic classification, which means it's a large, complex sunspot group with pronounced penumbral regions on both ends and a collection of intermediate spots scattered across its area. 26 individual sunspots in total. It occupies 170 millionths of the solar hemisphere. The position on April 4th was north 2 degrees, west 15 degrees, which means it was nearly centered on the disk as seen from Earth. From the Artemis crew's perspective, out past the Moon's orbit, the geometry was even more direct. The Space Weather Prediction Center assigned region 4409 a 15% probability of producing an X-class flare over the next 72 hours. 15% might not sound like much until you understand that most active regions on the Sun hover around 5% or less. Region 4409, right there in mid-April, was 3 times more likely to produce an X-class event than region 4405, which had already punched out an X-1.4 on March 30th. This is the first crewed mission beyond low Earth orbit in 53 years. Not since the final Apollo missions in 1972 has anyone in a spacecraft ventured into that region of space where the magnetosphere cannot protect them. The institutional memory is almost completely gone. The people who flew those earlier missions are either retired or dead. The mission planners, the engineers, the people who built Artemis II, they studied the old data, they ran the simulations, but they had never really had to confront the scenario where an impulsive flare detonates while the crew is 300,000 kilometers away from help, and now it had happened on flight day 4 with the rest of the mission still ahead of them. The question that nobody on the ground wanted to ask out loud was whether the shelter protocol designed for yesterday's understanding of solar physics could actually save these 4 people if the cork holding back region 4409 finally failed and released something larger. Part 2. The shelter protocol was built for yesterday's solar physics. To understand why the shelter protocol is breaking down as a concept, you have to understand the actual difference between the 2 types of solar flares, because the distinction is the difference between a problem you can solve and a problem you cannot. There are eruptive flares and there are impulsive flares, and they are not just variations on the same thing. They are fundamentally different phenomena, and the people who designed the Artemis Radiation Protection Plan knew the difference on paper, but had never had to confront the implications in real time with actual human beings in actual space. An eruptive flare is what most people think of when they think of a solar flare. A long-duration event, sometimes lasting for hours, magnetic field lines reconnecting, but the reconnection is powerful enough to lift plasma off the solar surface itself. That plasma accelerates upward, and often it escapes the Sun entirely, launching into space as a coronal mass ejection. The X-1.4 that region 4405 produced on March 30th was an eruptive event. It generated a halo CME, an ejection visible all the way around the solar disk. It produced a Type II radio burst with a shock front travelling at 1,872 km per second. When that CME arrived at Earth, it produced a G2 geomagnetic storm, the kind of storm that lights up auroras across the northern latitudes and makes the power grid operators very nervous. The crucial thing about the March 30th event was the warning timeline. The radio observations of the shock front told forecasters it was coming. The SOHO satellites provided imagery. The proton event started building on April 1st, and the geomagnetic impacts arrived on April 1st and 2nd. Hours upon hours upon hours of warning. Every system that anyone had designed to protect against extreme space weather was built on the assumption that you would have this kind of window. You would see it coming, you would prepare. An impulsive flare is the opposite. The magnetic reconnection is confined. The energy is not large enough to overcome the overlying magnetic field structure that holds the Sunspot group in place. So instead of launching into space, the energy gets released in a sudden burst, concentrated in the lower solar atmosphere. The radiation spreads outward at light speed. The particles accelerate not to escape the Sun but to high energies within a confined region. No CME, no slow build-up, just pure kinetic energy and electromagnetic radiation, converted and released, and then gone. The M7.5 on April 4th was this kind of event. So were the M1.7 at 7:58 that morning. So were the M1.2 at 12:11, and the M1.0 at 23:04. 4 separate impulsive flares from the same region in a single day. All of them too fast to shelter against. All of them arriving before you could react. Here is where the conversation gets into the realm of speculation and hypothesis, because the current understanding of why region 4409 was firing off these impulsive flares in rapid succession is not complete. One model that has some support in the literature is what researchers call the cork hypothesis, The idea is that the Sunspot group is sitting beneath a very strong overlying magnetic field, the kind of field structure that is powerful enough to prevent any erupting flux rope from escaping. Every time the reconnection happens, every time energy builds up and releases, it does so within a confined region. The overlying field acts as a lid. But here is the problem with that scenario. Every time the lid holds, every time an eruption happens inside instead of outside, some of the energy releases, but the overall configuration does not relax. The stored energy keeps building, the magnetic stress keeps increasing, the cork stays in place, but the pressure underneath keeps growing. What this means is that you can have a situation where multiple moderate impulsive flares precede a single, much larger eruptive event. The small eruptions are releases of pressure, but they are not enough to relax the system. They are the sound of the valve creaking open, and the cork could fail at any moment. It could fail with an X1, it could fail with an X5, it could fail with something larger than anyone has reliable data on, because we have not had instruments in space watching the sun continuously throughout the modern era. The last time something truly catastrophic happened, in 1859 we had only the naked eye and some telescopes. We knew there was an event. We did not know its actual magnitude. The crew was operating within a context of elevated space weather activity that went back weeks. A G3 geomagnetic storm on April 3rd, the strongest storm of the mission window, with a KP index of 6.67. That storm was driven by the eruptive events from region 4405 earlier in the cycle. The electron flux in the radiation belts peaked at 4,465 particle flux units, and the streak of elevated electron flux dated back to March 20th through 22nd, when other storms had pumped energy into the system. The Van Allen belts, the region that the Artemis spacecraft had to transit to reach lunar space, were more energetic than normal. The crew absorbed dose during that transit. They were already partway through the mission with some radiation exposure already recorded. Now, the way the shelter protocol actually works, when it works, is almost absurdly labour-intensive. The crew opens the storage bays beneath their seats. They remove the stowage bags that contain equipment, supplies, food, water, everything that is stored down there to save space in the cabin. They manually position these bags to form a barrier around the central habitation module. They do this while accelerating in orbit. They do this while trying to stay calm. The goal is to create a dense shield of whatever material they have available, food and water and equipment acting as radiation absorbers, surrounding the crew compartment. This process takes up to 1 hour. The Astrorad vest provides an additional layer of organ-specific protection, primarily to the blood-forming organs and the lungs, which are the tissues most critical for survival after acute radiation exposure. The vest does not protect the whole body. It protects the parts of the body that kill you most quickly if they are severely damaged. Donning the vest takes about 5 to 10 minutes, assuming everyone knows what they are doing, assuming nobody panics, assuming the vest is accessible and not buried under stowage that now needs to be deployed somewhere else anyway. The Space Radiation Analysis Group at Johnson Space Center monitors the real-time solar wind data from the GOES satellites, from the ACE satellite sitting near the L1.5 Lagrangian point, from DSCOVR, the Deep Space Climate Observatory, that provides early warning of incoming solar wind structures. For a CME event, for an eruptive flare with a halo ejector, the SRAG team can provide hours of warning. The interplanetary magnetic field orientation can be monitored, the velocity can be measured, the arrival time can be predicted to within minutes. But for an impulsive flare, the warning collapses. It collapses to minutes. It collapses to less than the time it takes to deploy a shelter. It collapses to a time frame where the instrument that detects the event is the instrument that announces it has already happened. There is also the question of single event upsets, a problem that most people never think about but that every spacecraft designer loses sleep over. A single event upset happens when a high-energy particle passes through computer memory, through the avionics that control the spacecraft and flips a bit. Not destroys the bit, not burns out the circuit. Just flips a single 0 to a 1 or a 1 to a 0. One bit in the right place can corrupt a command sequence. One bit in the wrong register can cause the spacecraft to execute a false command. During the August 1972 event, the one that happened between Apollo 16 and Apollo 17, if modern avionics had been present, the flight computers would have experienced hundreds of single event upsets, hundreds of random bit flips in the systems that actually control the spacecraft. Nobody knows how many of those bit flips would have been benign, and nobody knows how many would have led to catastrophic failures. But this is the kind of consideration that keeps mission planners awake at night. The radiation environment is not just a hazard to human tissue, it is a hazard to the systems that keep human beings alive. Part 3. Why Region 4409 changed everything on April 4th. Region 4409 was not just any active region. It was a complex, fully developed spot group with characteristics that made it one of the most dangerous locations on the solar surface at the time it was rotating toward Earth. The EAI classification means it was a mature, large group with clear penumbral structure at both its leading and trailing ends. The spots were spread across an area of 170 millionths of the solar hemisphere. That might sound small until you understand that the solar hemisphere is vast, that 1 millionth is an area roughly the size of Earth, and that 170 millionths means you're looking at a structure that could cover the continental United States 3 times over. 26 individual sunspots within the region, each one with its own field structure, each one capable of independent magnetic reconnection events. The beta-gamma magnetic classification was the key. This is a classification system that describes the arrangement of opposite polarity magnetic fields within the sunspot group. In a beta-gamma configuration, you have regions of opposite magnetic polarity separated by a single shear line, a boundary where the field reverses. This configuration is notoriously unstable. It is the kind of magnetic arrangement that does not like to stay quiet. It does not want to remain in equilibrium. Every model of solar flare initiation points to beta-gamma structures as the configuration most likely to produce large events, and region 4409, in its position north 2 degrees, west 15 degrees, was nearly centered on the solar disk as seen from Earth. The geometry was optimal. It was aimed directly at our planet. For a crew in deep space, the geometry was even more direct. The position matters more than most people realize. A sunspot group on the eastern limb of the Sun, rotating toward Earth, is less of a threat than one at disk center. The connection angles are different. The interplanetary magnetic field geometry changes. But a sunspot group at disk center, aimed directly outward, with no geometric mitigation, with a clear line of sight to everything in the inner solar system, is the most dangerous configuration possible. Region 4409 was at that position. It was aimed at the Artemis crew like a loaded gun at point-blank range. The Space Weather Prediction Center forecasts probabilities for the next 24 hours and the next 48 to 120 hours. When Region 4409 was at its most active, SWPC assigned it an 80% probability of producing at least one C-class flare, a 40% probability of M-class events, and a 15% probability of X-class. 15% over the course of 72 hours. The active region that had already punched the X1.4 on March 30th, Region 4405, had only a 5% X-class probability at the same time. That means Region 4409 was 3 times more likely to produce an X-class event than the region that had already demonstrated it was capable of exactly that. The 4 flares on April 4th, in chronological order, were the M7.5 at 1:17, the M1.7 at 7:58, the M1.2 at 12:11, and the M1.0 at 23:04. All impulsive, all confined, all producing no detectable CME, no halo ejection, no slow build-up that might give early warning. This pattern was significant because an M7.5 event frequently produces an associated coronal mass ejection. They are large enough that they usually overcome the confining field and launch plasma outward. The fact that the M7.5 from region 4409 did not produce a CME suggested something unusual about the magnetic structure. It suggested a very strong overlying field. It suggested that whatever was driving these eruptions was being held down by something extremely powerful. The Cork hypothesis, as it has come to be known in the literature, attempts to explain this scenario. Imagine a sunspot group with a dominant overlying magnetic field so strong that it acts as a lid, containing any eruptions that happen beneath it. Each time an eruption occurs, some energy is released, some stress is relieved, but the configuration does not fully relax. The overlying field remains in place. The pressure underneath continues to build. The next eruption occurs not because the stored energy went away, but because it accumulated again. And the next one after that. The pattern continues until at some point the pressure underneath becomes so great that the lid fails. When that happens, when that cork finally comes out, You do not get a small eruption. You get an event that releases all of the accumulated energy at once. The solar physicists watching region 4409 on April 5th noted something that seemed contradictory on the surface. The leader spots showed minor decay and slight separation from the main sunspot group, the kind of structural change that might suggest the region was winding down. But the scientists understood what this actually meant. Minor decay in a sunspot region doesn't signal safety. It often signals the opposite. When the larger magnetic structures that hold a region together start to loosen, the tension beneath builds. The magnetic field lines that were previously constrained begin to reorganize. This process of subtle disintegration can precede the most violent eruptions, because the magnetic configuration becomes increasingly unstable as the old structure breaks apart. Region 4409 was like a compressed spring inside a damaged container. The container wasn't holding as well anymore. On April 4th alone, region 4409 had produced 23 of the 24 flares that erupted from the entire visible solar disk. Every single M-class event that day came from this one region. 3 separate M-class flares in a single 24-hour period from a single location. No other region on the visible sun was producing anything close to this level of activity. Region 4409 had become the most prolific flare producer on the disk, and it remained dominant even as some of its visible structure showed signs of change. The question wasn't whether it was dying down. The question was what it would do next. This is the scenario that kept the radiation experts at NASA awake on April 4th and the morning of April 5th. Not the M7.5 that had already happened, not the flares that had already been absorbed and analysed and written down in the data logs, but the question of what comes next. How much energy is stored in region 4409? How much longer can the overlying field contain it? What is the actual probability that between April 5th and April 8th, the cork fails and releases something that makes an M7.5 look like a precursor? The crew was approaching the lunar flyby point scheduled for April 6th. That was the point of maximum distance from Earth, 252,757 miles outbound. That was the point where they would be farthest from any possible rescue, farthest from any possible evacuation scenario, farthest from Earth's magnetosphere and any protection it might offer. If region 4409 produced an X-class impulsive flare in the next 72 hours, the odds were good that it would happen while the crew was near that point of maximum isolation. The mission had 250 milligrays equivalent to blood-forming organs as a career exposure limit baseline. 250 milligrays equivalent is roughly the point where radiation sickness becomes a serious concern, where the recovery timeline becomes measured in months rather than weeks. The current threshold that triggers NASA's mission radiation protocol is 250 milligrays, equivalent to the blood-forming organs. A significant dose from an X-class impulsive event, even absorbed within the Orion shelter, could put the crew across that threshold. The Space Weather Prediction Center issued a proton event alert on April 4th at 01:35 as the initial flux from the M7.5 began to arrive at Earth. The greater than 1 mega-electron-volt proton flux had peaked at 431.2 particle flux units at 2:45 in the morning on April 4th. That was significant. The SWPC threshold is 10 particle flux units, the lower boundary of what counts as a significant proton event. The crew, at 169,000 miles away, would have received a different environment than Earth, but the magnitude was already substantial. SWPC forecasts indicated a 20% probability of S1 conditions, significant proton events, between April 5th and April 7th. 20% might not sound like much, but when you are talking about events that carry risk to human life, 20% is not a background probability. It is a meaningful chance. Part 4. The Worst Case Escalation. Tier 1. X-Class from Region 4409. The threshold between M-Class and X-Class is not a large jump in absolute terms, but it is a distinct one. An X1.0 flare is 1.33 times more energetic than an M7.5. That 1.33 factor means that an X-class event produces particles with higher energies, higher flux densities, and longer-lasting effects than the M-class events that had already impacted the crew. If region 4409 produced an X1 to X3 range impulsive flare, the energetic proton flux would cross the S1 threshold, reaching 10 particle flux units at greater than 10 mega-electron volts, possibly crossing into S2, 100 particle flux units. At those flux levels, the Orion shielding, 20 grams per square centimetre at the critical blood-forming organs, would be adequate. The dose would not be immediately lethal. It would not produce acute radiation syndrome so severe that the crew could not complete the mission. But the dose would be substantial, and it would accumulate on top of the exposure already received from the G3 storm, the elevated electron flux environment, and the galactic cosmic ray background that no amount of shielding can completely eliminate. The worst scenario, the one that mission planners did not want to think about but had to, was an X5 to X10 impulsive flare. That kind of event could produce S3 proton conditions, more than 1,000 particle flux units at greater than 10 mega-electron volts. Or even S4, more than 10,000 particle flux units, the kind of proton environment that does not often occur, that the records do not capture in any detail because it almost never happens. At S3 levels, the crew would definitely need the shelter deployed. Staying inside the central module with the stowage bags arranged around them would be critical. Even so, the dose rate would be severe. The crew would accumulate a significant fraction of their yearly radiation allowance, possibly their career limit, in the span of hours. At S4 levels, at an extraordinary proton event, the situation moved from dangerous but survivable into territory where even inside the most heavily shielded part of the Orion, the dose rate would become problematic. The crew would be watching the radiation meter climb in real time, aware that they were accumulating dose faster than anyone had anticipated in the mission profiles, aware that if the flare lasted for hours, or if multiple events occurred, they could exceed their career exposure limit during the mission itself. The critical problem with impulsive flares is the compressed timeline. A coronal mass ejection, an eruptive event, starts accelerating before the light travel time begins. An X-class eruptive flare can produce radio bursts and electromagnetic effects that are detected on Earth within minutes. The interplanetary magnetic field signature and the solar wind velocity can be measured. An arrival time can be calculated. The crew can begin deploying shelter protocol with full knowledge of what is coming and when it will arrive. They have hours. With an impulsive flare, they have the moment of detection, the moment when the first radiation arrives, and that is it. The shelter protocol that takes up to 1 hour to deploy cannot be deployed. The Astrorad vest that takes 5 to 10 minutes cannot be donned before the first particles cross the spacecraft. You're already inside the event by the time you know it has happened. The crew was approaching the lunar flyby on April 6th, which meant they would be at their maximum distance from Earth on that date, 252,757 miles outward. The geometry became worse as they moved farther from Earth. The Artemis trajectory takes the spacecraft in a wide arc around the Moon, and the crew would not begin their return leg until April 7th. For a 72-hour window starting April 5th, the crew would be at or near maximum distance, at the point where the only protection was the spacecraft itself, and whatever they could improvise. If the cork in region 4409 failed during that window, if the accumulated magnetic energy released as an X-class or larger impulsive flare, the crew would be stuck in the worst possible scenario. The 15% X-class probability over 72 hours, when extrapolated across the remaining 6 days of the mission profile, climbed to somewhere in the range of 25 to 30% cumulative probability. That means the actual risk that an X-class flare would occur at some point during the mission was closer to 1 in 4 than 1 in 6. Those are odds that professional risk assessors take very seriously. Those are odds that trigger conversations about mission abort, about whether to attempt to accelerate the return trajectory, about whether to put additional resources into developing better shelter protocols or abandoning the mission profile altogether. An X1 to X3 impulsive event was survivable, uncomfortable, but survivable. The crew would accumulate dose. There would be long-term health consequences possibly, increased cancer risk, possible cognitive effects, but they would come home, they would be alive. An X5 to X10 event was the threshold where survivability became questionable. This was the tier where even inside the shelter, even with the best shielding and the densest possible barrier of stowage between them and the radiation, the crew would be in serious danger. This was the tier where mission parameters started moving from risk mitigation to crisis management. And this was just Tier 1. This was just one active region on the Sun, just the kind of event that region 4405 had already demonstrated was possible, just the medium-term escalation within the current solar maximum. There were 3 more tiers, and each one opened doors onto scenarios that made Tier 1 look manageable. Part 5. Why more shielding can actually make things worse. Here is where the conversation gets into some of the most counterintuitive physics that confronts anyone trying to protect human beings from space radiation. And here is where the situation with Artemis II moves from dangerous into something approaching genuinely paradoxical. More shielding, under certain circumstances, can actually increase the radiation dose that a person receives. This is not intuitive. It is not how anyone's brain naturally processes the concept of protection. But it is how the physics works, and it is one of the reasons why deep space radiation protection remains one of the most unsolved problems in human spaceflight. At lower energies, below about 100 megaelectronvolts, the relationship between shielding and dose is exactly what common sense would predict. More material means lower dose. This is straightforward, predictable, and the basis for the conventional understanding of radiation protection. The shielding material absorbs particles. The particles lose energy passing through the material. The dose is reduced. This is why hospitals use lead aprons during X-ray procedures. This is why nuclear power plants are surrounded by concrete. Below 100 megaelectronvolts, the relationship is linear and understandable. Above 100 megaelectronvolts, something different happens. The high-energy protons, the particles that carry the most danger in the most extreme solar events, start interacting with the nuclei of the shielding material itself. They collide with aluminum atoms, with polyethylene molecules, with whatever material the spacecraft is constructed from. When they do, something called spallation occurs. The proton hits the nucleus fragments, and the collision produces secondary radiation. Neutrons scatter outward. Gamma rays are released. The original particle is absorbed, but in its place you get a different set of particles, often with different energy distributions and different biological effects. Neutrons are particularly insidious because they have no charge. An electrically charged particle, like a proton or an alpha particle, interacts constantly with the electrons in matter. It loses energy through countless small interactions. A neutron, being neutral, does not interact with electron clouds. It passes through matter almost as if the matter is not there, penetrating deep into biological tissue, travelling through the human body almost unimpeded. When a neutron finally does interact with a nucleus inside the body, when it causes nuclear damage directly in DNA or in chromosomes, the biological effect is severe. The relative biological effectiveness of secondary neutrons, the RBE value that measures how much damage they cause per unit dose, is 10 to 20 times higher than primary protons. This means that a dose of secondary neutrons is 10 to 20 times more likely to cause cancer, genetic damage, or acute radiation sickness than an equivalent dose of primary protons. This is the shielding paradox in its clearest form. The Orion spacecraft provides approximately 20 grams per square centimetre of shielding at the crew compartment, primarily from the structural material, the water tanks, and the internal equipment. This is a significant improvement over the Apollo capsules, which had only 7 to 10 grams per square centimetre. The improvement was deliberate, designed to be better, designed to protect the crew more effectively. And for most of the radiation environment that Orion might encounter, it does. For the kind of proton fluxes that produce S1 or S2 conditions, the 20 grams per square centimetre shielding is excellent. It absorbs the bulk of the incoming flux, and the secondary radiation produced is minimal and manageable. But if region 4409 produces an X5 to X10 impulsive flare, the situation changes. The highest energy component of the proton spectrum, the relativistic tail, the particles moving at greater than 80% of light speed, will interact with that 20 grams per square centimetre of shielding and produce secondary neutrons at a rate high enough that the biologically effective dose inside the spacecraft might actually be higher than it would be in an unshielded location. The shielding that was designed to protect them becomes paradoxically less effective. In some models, it becomes counterproductive. The Astrorad vest, which provides additional organ-specific protection against lower energy protons by directing them around critical tissues, provides no protection against secondary neutrons. Secondary neutrons pass through the vest as if it is not there. They penetrate to the blood-forming organs, to the lungs, to the bone marrow, exactly the tissues that the vest is designed to protect. This is not a flaw in the design. This is a fundamental limitation of physics. There is no material, no configuration, no amount of thickness that can protect equally well against the entire spectrum of cosmic radiation. Below a certain energy threshold, more shielding helps. Above that threshold, shielding becomes a liability. The spacecraft designers chose the optimal thickness, the point where the improvement from blocking primary protons outweighs the increase in secondary radiation. 20 grams per square centimetre is close to optimal for the radiation environment that most missions encounter. But close to optimal is not perfect, and it is certainly not adequate if the environment exceeds the design parameters by a factor of 10 or more. This is precisely the scenario that an X5 to X10 impulsive flare from region 4409 would create. An environment so extreme that the fundamental assumptions of the radiation protection architecture become questionable. An environment where the shield that was designed to protect the crew becomes less useful, where the best protection against an impulsive X-class is not better shielding or better vests, but rather simple physics, not being in the path of the flare. The Artemis II crew does not have that option. They are committed to their trajectory. They are 3 days into the mission. They are 400,000 kilometers from home, moving at 1.5 kilometers per second relative to Earth. They cannot turn around and run. They cannot ask the sun to wait. They can only hope that region 4409 remains stable, that the cork holds, that the next 3 days pass without the catastrophic failure that the numbers suggest is now possible. But those numbers, 15% probability, are not reassuring odds when you are the crew in the spacecraft. Those are the odds of a lottery you do not want to win. And what we have been discussing so far, the M-class flares, the X-class scenarios, the Tier 1 escalation that can happen from a single active region, is only the beginning. Because the Sun is capable of something larger still. The Sun is capable of events so large that they break the entire framework of modern solar physics, events that have happened before and will happen again. And when one does, when the Sun truly loses control, the difference between Artemis II's radiation environment and unsurvivability becomes not a matter of degree but a matter of luck. Part 6. The comet nobody is talking about. There's something happening that almost nobody is talking about, and that's exactly the kind of thing that keeps me up at night when I'm trying to understand what's really going on out there. On April 4th, the same day region 4409 fired the M7.5 flare directly at the Artemis II crew, something else crossed the inner solar system. A comet. Not some ordinary leftover chunk from the Oort cloud making a predictable journey around the Sun. This one came closer to the solar surface than any tracked object has come all year. We're talking about Comet C 2026A1, discovered by the Mount Abu Planetary Observatory survey back in early March, moving on a parabolic orbit that suggests it might be making its first visit to the inner solar system in potentially millions of years. It reached perihelion on April 4th at 0.00573 astronomical units from the Sun. Let me translate that into something you can actually visualize. That's 857,000 kilometers from the solar photosphere. To put it another way, the comet came within 1.23 solar radii of the Sun's surface. That is extraordinarily close. For context, the orbit of Mercury sits at about 0.39 astronomical units. This comet punched through to inside Mercury's orbit and grazed the solar atmosphere itself. Now, I need to be careful here because there's a lot of speculation that gets thrown around about sun grazers and solar activity, and most of it isn't supported by the actual physics. But there is a legitimate observation that's been made over the past 2 decades from the SWPC spacecraft, which has been watching Kreutz Group sun grazers since 1995. Multiple researchers have documented temporal associations between sungrazer passages and CME activity. Not causation, not a proven mechanism, but a pattern, a coincidence that recurs often enough that it's worth noting. The comet's trajectory was parabolic, meaning eccentricity of 1.0, which means this thing wasn't perturbed by the planets. It came from the Oort cloud, or at least from the outer solar system, on a genuinely fresh trajectory. And yes, I understand that conspiracy theorists are already saying NASA knew about the comet and launched Artemis II anyway. That's the kind of speculation that spreads fast because it sounds plausible. But the reality is simpler and weirder. NOAA's forecasts don't model cometary interaction. There's no established heliophysical mechanism by which a small body passing near the Sun would directly trigger a specific flare event on the photosphere. The variables are too many, the interactions too complex. The solar dynamo doesn't work on cometary timescales. But here's what matters. Whether the comet had anything to do with Region 4409's activity or not, it's a reminder of how many variables are actually in play while 4 human beings are sitting 169,000 miles from home with no way to come back early. The comet is a curiosity, a weird data point, a coincidence that happened to occur on the same day as the flare. But what I want you to understand right now is that we're about to pivot from discussing what's happening right now to discussing what could happen next, and that shift is critical. The events I'm about to describe aren't immediate threats, they're tier-class escalations, and they're drawn from the most complete historical records we have about what the Sun is actually capable of. Part 7, Tier 2, What Happened in 1859. Let me take you back to September of 1859, September 1st to be specific. A man named Richard Carrington was observing the Sun through a telescope at his private observatory in Red Hill, England, and he saw something that hadn't been documented in human history before: a sudden brightening on the solar disk, not a feature of the corona that only shows up in eclipse. A white light flare visible in ordinary sunlight through a regular telescope against the photosphere itself. Carrington was recording what he saw, tracking the flare as it evolved, and within minutes it faded. That same day, independently, another astronomer named Richard Hodgson at a separate observatory in London saw the exact same phenomenon. They didn't know each other. They were observing the same event from 2 different locations. They verified it: a white light solar flare, recorded in real time by human observers using pre-photographic instruments. What happened next is where this gets significant. The coronal mass ejection that accompanied that flare travelled from the Sun to Earth in approximately 17.6 hours. That speed is extraordinary. Modern coronal mass ejections usually take between 2 and 4 days to reach us. For a CME to arrive in under 18 hours means it was travelling faster than 2,500 kilometers per second. An absolutely ferocious ejection. And when it hit Earth's magnetosphere, it triggered the most intense geomagnetic storm in the entire instrumental record. Auroras were visible within 23 degrees of the geomagnetic equator. That meant auroras in Cuba, auroras in Hawaii, auroras in Colombia, auroras visible in southern Japan and Queensland, Australia. The night sky was bright enough to read a newspaper by, and on the ground, telegraph systems across Europe and North America failed catastrophically. We're talking about approximately 200,000 kilometers of telegraph lines that simply stopped working. Operators received electrical shocks, equipment caught fire, and most tellingly, after the lines were physically disconnected from their power sources, they continued sending and receiving messages. The signals were being driven by geomagnetically induced currents flowing directly through the Earth itself. The system was broken, but it wouldn't stop transmitting because the electromagnetic environment had been so thoroughly disrupted that the ground itself was conducting electricity. The financial impact of a Carrington-class event today would be staggering. Lloyd's of London published an analysis in 2013 that estimated the damage to the United States alone would fall between $600 billion and $2.6 trillion. Globally, the recovery cost over 5 years would be approximately $2.4 trillion. Supply chain disruption alone would cost between $2.4 and $3.4 trillion, which translates to between 3.9 and 5.6% of global GDP. We're not talking about a localized regional event. We're talking about something that would reshape the global economy for years. Now let me connect this back to the Artemis II crew. If Region 4409 produced a Carrington-class event, it would produce something that an ordinary X-class flare doesn't. It would produce 2 distinct phases of radiation assault separated by time. The first phase is the impulsive pulse, which arrives in approximately 8 minutes. That's the particle cascade we've already discussed. The second phase is the CME arrival, which would come between 15 and 20 hours later, and that produces a sustained radiation storm lasting 24 to 48 hours. The crew could potentially shelter before the second phase arrives, but they would already be carrying the integrated dose from the impulsive phase. The total accumulated exposure during both phases could approach or exceed 250 millisieverts equivalent biological effectiveness, which is approaching the threshold where permanent organ damage becomes a near certainty. What makes Region 4409 particularly concerning in this context is its location on the solar disk. It's at disk center. That means if it produces a Carrington-class event, the eruption would be pointed almost directly at Earth. The geometry is perfect. The probability of such an event happening during the Artemis II mission window is low. I'd estimate it at somewhere between 0.01 and 0.03%, which translates to 1 in 3,000 to 1 in 10,000. But it is not zero, and that's the important phrase right now. It's not zero. It happened once in recorded history, and there is absolutely no reason to believe it couldn't happen again, because in 2012, it almost did. Part 8. The 2012 near miss that nobody talks about. I want to tell you about an event that nearly ended everything. On July 23, 2012, an active region that was tracked as 1520 produced a massive coronal mass ejection. Not an X-class flare necessarily. The classification isn't the point is the ejection speed. The CME reached velocities exceeding 2,500 km per second. That's Carrington-class speeds. And this ejection was detected by NASA's Scarier spacecraft, which was positioned ahead of Earth in its orbital path, stationed where it could observe solar activity from a perspective that's shifted by 90 degrees from Earth's viewpoint. Scarier A measured the leading shock wave at approximately 3,300 km per second. The ejected coronal plasma behind the shock was travelling between 1,800 and 2,200 km per second. The event was absolutely immense. But here's the critical detail. The CME crossed Earth's orbital path approximately 9 days after Earth had passed through that point. Let me emphasise that. Not before, after. Earth had already moved past the location where this Carrington-class event would have impacted. If the eruption had occurred just 1 week earlier, the timing would have been different. The CME would have reached Earth's orbit during a 9-day window when Earth was still there. It would have hit us directly. Daniel Baker from the University of Colorado Boulder published the analysis in a paper in the journal Space Weather in December of 2013. He concluded that the 2012 near-miss CME was comparable to, or possibly stronger than, the 1859 Carrington event. Baker's exact words were that if the eruption had occurred only 1 week earlier, Earth would have been in the line of fire. He described it as a cosmic close call. Think about what that means. We exist in a universe where we've already experienced 2 Carrington-class events in the modern era. One happened before we had electricity, and one happened during an era when we had satellites and power grids and 17,000 power plants and a global communication system depending entirely on electromagnetic infrastructure. The second one missed us by 9 days, by a little more than the time it takes light to circle the sun twice, by the difference between one solar rotation period and another. And here's what really should concern us. 2012 occurred during solar cycle 24, the cycle that ran from approximately 2008 to 2019, and which was, by modern standards, relatively weak. The cycle was predicted to peak at about 130 sunspots. It actually peaked at around 125, below expectations but not dramatically. We're currently in solar cycle 25, which started in December of 2019, and this cycle is overperforming. The sunspot number, which is the standard metric used to measure solar activity, has already exceeded 200 in several observations, compared to a pre-cycle prediction of approximately 115. We're already running about 75% higher than expected, which means we're in a more active solar environment right now than we were in 2012, which means the probability of a Carrington-class event in the next 3 years is higher than it was in 2012. The Artemis II crew is 169,000 miles from Earth's magnetosphere. There is no magnetic shield between them and the Sun. Region 4409 is at disk center, and there is a 15% probability that it escalates to X-class within the next 3 days. And we know from the 2012 near-miss that a Carrington-class event in the modern era is not a theoretical exercise. It's something that almost happened within the living memory of people who are still alive today. A cosmic coin flip that came up heads instead of tails, and we didn't even notice because most people on Earth weren't paying attention to the solar wind data. But tree rings and ice cores have a lot more to tell us about what the Sun is really capable of when it truly wants to lose control. Part 9, Tier 3. The Miyake Events. When the Sun truly loses control. Everything I've described so far exists within a very specific temporal window, the 165 years of continuous solar observation that started around 1850, give or take. We have the 1859 Carrington Event. We have detailed records from the 2012 near-miss. We have satellite data going back to the 1970s. We have instrumental records spanning most of the last 2 centuries. But the Sun has been operating for 4.6 billion years. And it turns out the tree rings and ice cores have a lot more to tell us about what the Sun is really capable of when it truly wants to lose control. In 2012, a Japanese physicist named Fusa Miyake was studying the annual growth rings of Japanese cedar trees, trying to extract historical climate information from the width and chemical composition of tree rings. And she found something unexpected: a sharp spike in radioactive carbon-14 in rings dated to 774 to 775 AD. Not a gradual increase over several years, a sudden dramatic spike appearing in a single year's growth ring. The spike was so enormous that it couldn't be explained by any ordinary process. You can't get that kind of concentration change from volcanic activity. You can't get it from changes in the cosmic ray background. The only thing that could produce an influx of carbon-14 that large and that sudden would be an extraordinary burst of cosmic radiation from the Sun, producing high-energy particles that cascade through the atmosphere and transform nitrogen-14 into carbon-14 across the entire planet within the span of a few months. Miyake's finding was independently confirmed. Scientists checked beryllium-10 in ice cores. They checked chlorine-36 in the same cores. Multiple isotopic markers all pointed to the same conclusion. In the year 775 AD, the Sun produced an event so powerful that it left a measurable signature in the geochemistry of the entire planet. And when researchers started looking more carefully at the tree ring record, they found it had happened before, multiple times. At least 6 confirmed Miyake events in the documented tree ring record: 7,176 BCE, 5,410 BCE, 5,259 BCE, 660 BCE, possibly as far back as 664 BCE, 775 AD, 993 AD. And there's a 7th one that was even more recent than we initially thought, discovered in 2023 when scientists examined ancient trees recovered from eroded banks near the town of Gap in the southern French Alps. The tree ring record from around 12,350 BCE showed the largest Miyake event ever documented, bigger than 775 AD, bigger than any of the others. The historical Miyake events exist in the scientific literature, documented and cross-referenced, but they also exist in a state of genuine uncertainty. Not all researchers agree on what they represent. Some scientists have questioned whether every one of these events truly originated from the Sun. When researchers examine larger tree ring samples collected from multiple locations across the globe, they found something unexpected. The polar enhancement that would be expected if a solar flare delivered cosmic rays to Earth wasn't as pronounced as the models predicted. The signal looked strange when examined closely, inconsistent with what the physics should show. There's another anomaly that troubles the researchers. Miyake events appear at random points in the solar cycle, not clustered at solar maximum where the most powerful flares typically occur. Solar flares follow the 11-year cycle. They cluster during periods of high solar activity. Miyake events don't follow this pattern. They arrive when they choose. If they're solar flares, they shouldn't behave this way, but the weight of evidence still points to solar origin. No other phenomenon fits the signature as well. The uncertainty about Miyake events makes them worse, not better. Because if they're not purely solar flares, then they're something else. And if they're something else, we understand them even less. The 775 AD event is considered the reference standard, the one that papers cite when they talk about Miyake events. And the estimates for its magnitude are staggering. Conservative estimates suggest it was approximately 10 times more powerful than the Carrington Event. Other calculations suggest it could have been 50 to 100 times stronger. The energy equivalent, assuming a typical solar flare spectrum, is approximately 660 billion times the energy released by the Hiroshima atomic bomb as cosmic rays, released into the solar system, in what was probably a single event lasting hours to at most days. Now let me connect this directly to the Artemis II crew. If region 4409 produced a Miyake-class event, there is no scenario in which the crew survives it. No amount of polyethylene shielding, no water walls, no aluminum hull. The mass budget of the Orion spacecraft is not designed to attenuate a flux 10 to 100 times more intense than the Carrington Event. The cumulative dose would be tens of thousands of millisieverts, multiple orders of magnitude above the lethal threshold. The onset of acute radiation syndrome would begin within minutes. Nausea and vomiting would start almost immediately. Cognitive impairment and neurological damage would begin within hours. Lethal damage to bone marrow and the gastrointestinal system would progress over days until organ failure became inevitable. There is no medical intervention that would matter. There is no amount of hydration or electrolyte management that would stop the cascade. For Earth's technology, a Miyake-class event would be equally catastrophic, but in a different way. Every satellite in orbit would be destroyed or rendered inoperable. The power grid transformer damage would occur on a continental scale. Telecom systems would fail. GPS would be unavailable. Aviation would be grounded. The internet would simply cease to exist for years, not months. Recovery would require reconstruction of a substantial portion of Earth's technological infrastructure. We're talking about a decade-long process, potentially longer. The probability of a Miyake-class event occurring during the Artemis II 10-day mission is approximately 0.0003%, 1 in 300,000. NASA cannot plan for that, can't build a spacecraft for that, can't even reasonably insure against that. It's accepted as a background risk, similar to an asteroid impact occurring during launch, as a statistical fact of living in the universe. But it's real. It's happened at least 6 times in the tree ring record, possibly 7, and it could happen tomorrow, it could happen today, it could happen during the 15% window when region 4409 is escalating from M-class to X-class. The probability is infinitesimal, but it's not zero. And when you're 4 human beings 169,000 miles from home with no way to come back early, the difference between infinitesimal and zero starts to matter in a way that's hard to explain to people who are sitting safely on the ground. Region 4409's M7.5 is a data point on a spectrum. At one end of that spectrum, the flare is manageable. The crew shelters, the event passes, life goes on. At the other end of the spectrum is unsurvivable. There is no shelter. There is no protocol. There is no recovery. There is only the physics of the sun asserting itself without mercy. The Artemis II crew is somewhere on that spectrum right now, and we don't know where. But these are theoretical calculations. What happened in August of 1972 between Apollo 16 and Apollo 17 showed us exactly what a near miss looks like for a human crew. Part 10. The August 1972 Apollo Gap. 54 years ago, the Sun showed us exactly what this situation looks like when it happens in real time. The closest historical analogue to what the Artemis II crew is experiencing right now happened during the summer of 1972, and it's something that almost nobody remembers because the mission planners did exactly the right thing at exactly the right time, and when you execute a response correctly, the crisis disappears from the historical record. Apollo 16 launched on April 16, 1972, and returned on April 27, 1972. The astronauts were in space for exactly 10 days, almost the same mission profile as Artemis II. They came home safely. Apollo 17 launched on December 7, 1972, which was well after the situation I'm about to describe had completely resolved. Between those two missions, there was a gap, roughly 3.5 months with no crewed missions to the Moon. That gap wasn't random, it was deliberate. On August 2nd through 4th of 1972, the Sun produced a series of intense solar flares that generated particle fluxes exceeding 70,000 particles per second per steradian per square centimetre at energies above 10 million electron volts. That rating places it at S5 on the solar energetic particle scale, which is the highest category. Extreme. The August 4th flare alone produced a radiation dose rate of 241 rem per hour at the spacecraft shielding threshold, sustained at least at 45 rem per hour for half a day. To understand what that means, let me give you the NASA analysis from the time. An astronaut who was outside the spacecraft during EVA, in a spacesuit with minimal shielding, would have received approximately 4,000 millisieverts, which translates to 400 rem. That dose level places an unprotected astronaut squarely in the range of acute radiation syndrome, with a high probability of fatal outcome within days. Inside the Apollo command module, which had approximately 7 to 10 grams per square centimetre of aluminum shielding, the dose at blood-forming organs was attenuated to less than 350 millisieverts, still in the range where acute radiation syndrome is probable, but where survival and eventual recovery becomes possible. The margin between inside and outside the spacecraft was the difference between survivable and unsurvivable. That's a thin line. Now, Orion provides approximately 20 grams per square centimetre of shielding, which is a significant improvement over Apollo. It's roughly double, but shielding doesn't scale linearly with particle energy. At the highest energies, hundreds of million electron volts and above, no practical spacecraft shielding can stop the particles completely. They punch through. They lose energy, sure, but they deposit that energy in the structure and the human tissues. And then the secondary radiation paradox kicks in again. The higher the shielding, the more secondary particles are generated, and sometimes that secondary radiation is more dangerous than the primary particles were to begin with. John Young commanded Apollo 16. He walked on the moon during that mission. Years later, when he was asked about the August 1972 solar event that had erupted between his departure from Earth and the next crew's arrival, Young said something direct. They had been lucky. That was all there was to it. He didn't elaborate or minimize the danger. They had been lucky, and that was the simple truth. What Young understood, and what the radiation specialists had calculated precisely, was that the flare sequence hadn't been a single explosion. It was a series of eruptions that began on August 2nd and continued through August 11th, a chain of increasing violence that went on for more than a week. The worst came on August 4th. On that date, a flare erupted from the Sun that was classified retroactively by solar physicists as approximately equivalent to an X30 magnitude event. X30. The strongest flares ever measured by modern instruments have been X28. This event had been worse than anything captured in the instrument record, and it had erupted while the gap between crewed missions left no astronauts exposed. They had been lucky. Young knew something else too. August 1972 had occurred during solar cycle 20, a moderate cycle by the standards of solar activity. Solar cycle 25, the cycle that region 4409 belonged to, was significantly stronger. The average flare productivity was higher. The magnetic field at the Sun's surface was more energetic. If an event like August 1972 happened now, it would happen in a more volatile solar context. In 1972, nobody knew the August event was coming. It wasn't predicted. It was detected by ground monitoring after the fact, which means if Apollo 17 had launched in early August instead of December, the crew would have been caught in the radiation storm. They would have been in transit between Earth and the Moon during an S5 particle event. Inside Orion, they would have experienced approximately 400 to 500 millisieverts, depending on the exact geometry of the event and their trajectory. That dose is survivable, painful, problematic, but survivable. But combined with other doses from future missions, it begins to accumulate. The concern is total career dose for astronauts who fly multiple missions, and also the long-term cancer risk from accumulated radiation exposure. After 1972, NASA added solar monitoring to the launch constraints. The agency started tracking solar activity in real time and began building models to predict when the next major event might occur. This was the birth of space weather forecasting. Artemis II is the first crewed mission beyond low Earth orbit launched, since solar activity reached the levels we're currently experiencing. We're back at the same statistical probability of major events that existed during Apollo, but with better monitoring, better forecasting, and better spacecraft shielding. Here's what's important. We know human crews can be caught in solar storms because it almost happened in 1972. The Sun does not schedule its outbursts around mission timelines. The Sun doesn't care that there's a spacecraft full of humans crossing the void. Region 4409 sites at disk center with a 15% probability of escalating to X-class, and it sits there while the crew is farther from Earth than any human in 53 years. The crew can shelter. The Orion capsule is designed to handle X-class radiation. But if region 4409 escalates beyond X-class, if it produces something that the 15% probability space doesn't cover, the margin of safety shrinks. It shrinks fast. And there's another factor making this moment more dangerous than anything Apollo faced, and it has to do with what solar cycle 25 has been doing for the past 2 years. Part 11. Solar cycle 25 is overperforming, and nobody adjusted the mission risk. Let me take you back to 2019 for a moment. That's when the National Oceanic and Atmospheric Administration and NASA got together and made a prediction about what solar cycle 25 would look like. They pooled their expertise, ran their models, analysed the historical data, and they came to a consensus. The peak of this solar cycle, they said, would arrive around July of 2025, and when it did, The sunspot number would hit approximately 115. That was their forecast. 115. That was the number that solar physicists, mission planners, and risk assessors used to build the framework for Artemis II's launch window. But here's the thing about solar predictions. They're educated guesses, and sometimes the sun doesn't read the forecast. In March and April of 2026, right now, the actual observed sunspot number is over 200. 200. That's not a minor miss. That's not a 5 or 10% overshoot. We're talking about 70% above the prediction, nearly double what they said it would be. The sunspot numbers are climbing so aggressively that solar cycle 25 is now the strongest cycle in 2 decades. The last time we saw activity at this level was way back in the 1970s and 80s, during solar cycle 21. We're talking about a genuinely powerful solar maximum, not a moderate one. Now let's think about what that actually means. Every solar flare you've ever heard about, every coronal mass ejection, every radiation storm that threatens satellites or the power grid, their frequency goes up with solar cycle intensity. A strong cycle doesn't just mean more flares. It means more powerful flares, a higher probability of X-class events, and a higher probability of extreme events that can reach into the Carrington or Miyake territory. Region 4, 1409 didn't just randomly appear on the solar disk. It appeared on a sun that was running nearly 70% hotter than anyone predicted. It emerged from a solar environment that was dramatically more active and energetic than the model said it would be. And here's where the mission planning gets uncomfortable. Artemis II was designed and scheduled years ago. The launch window opened at a time when everyone expected solar cycle 25 to be behaving itself, cruising along at a respectable 115 sunspot numbers. Nobody planned this mission expecting the cycle to blow past 170, 180, into the 200s. The crew is flying into space during what turned out to be an unexpectedly violent solar maximum. NASA knew this was happening. They've been tracking the overperformance in real time, but they also knew that delaying the mission indefinitely until solar activity calmed down would mean waiting years, maybe longer. I know what some of you are thinking right now. You're thinking, this is a conspiracy. NASA knew the solar cycle was this aggressive, and they launched anyway because they wanted to beat a deadline or hit a political target. And I get why that narrative is attractive. It's the kind of story that makes sense in a certain framework. But here's the counter to that. NASA conducted extensive risk analysis before this launch. The Orion spacecraft was designed with radiation protection specifically in mind, knowing that solar activity was the major threat to crew safety. And here's something else. There's a real scientist, Dr. Velasco Herrera, who actually did recommend delaying Artemis II. That recommendation is publicly available. It's not a secret. But the decision was made to proceed, and that decision was based on rigorous risk assessment, not hidden agendas. The institutional reality is this. You can never eliminate solar risk by waiting. You can only manage it. And the risk assessment that NASA performed said that Orion's design, the crew's training, and the shelter protocols made this mission acceptable. Not riskless. Nobody's saying riskless, but acceptable. Here's the critical callback that I need you to hold on to, because this changes how you interpret every probability number I've mentioned tonight. The 15% probability of an X-class flare over the next 3 days, that's calculated against models that underestimated this solar cycle by almost half. The 0.03% probability of a Carrington-class event. The 0.0003% probability of a Miyake-class unsurvivable event. Every single one of those percentages was generated using solar physics models that predicted a moderate solar cycle 25. Those models have already been shown to be wrong by nearly 70%. That doesn't mean we should panic, but it does mean we should be very careful about treating those percentages as gospel. The sun we're watching right now is not the sun that solar physics predicted it would be. It's hotter, it's more active, it's more unpredictable, and the crew of Artemis II is flying toward it with probabilities that were calculated against a model of a calmer version of this star. But here's what's strange about probabilities. They're one thing when you're looking at them on a chart. They're something entirely different when you apply them to actual human beings in an actual spacecraft. Because probabilities exist in this abstract mathematical space, where everything averages out in the long run. But the crew doesn't live in the long run. The crew lives in the next 10 days. The crew lives right now, at this specific moment, with a specific spacecraft, at a specific distance from Earth, during a specific window in a solar cycle that nobody predicted accurately. Which brings us to the next piece of this puzzle. Because the probabilities are one thing, but the mission timeline, the actual geometry of where those 4 humans are in space and where they're going, that's where probability becomes reality. Part 12. The mission timeline trap. Maximum distance on April 6th. Right now, at this moment in time, April 4th, well into the afternoon in Houston, the crew of Artemis II is approximately 169,000 miles from Earth. That's flight day 4, they're 3 days into a 10-day mission, and they're getting farther away by the hour. Tomorrow night, April 6th, at approximately 7:05 in the evening, the crew will reach their maximum distance from Earth, 252,757 miles. Let me put that in perspective for you. The Apollo 13 crew in 1970 holds the record for the farthest humans have ever travelled from Earth. They were at approximately 248,000 miles from our planet when their oxygen tank exploded. The Artemis II crew will surpass that record by 4,102 miles. They will be the farthest humans from home since the Apollo era. They will be farther from Earth than most people on this planet will ever be, farther than most people's minds can even comfortably grasp, and they'll reach that maximum distance during their lunar flyby. The spacecraft will pass within approximately 7,000 miles of the lunar surface, far enough to give them a stunning view of the moon, close enough to feel the gravity well, close enough to take measurements and data that will be worth their weight in gold for future lunar missions. It's a critical part of the mission profile. It's the moment where Artemis II proves that the spacecraft can navigate to the moon with human pilots. Just hours ago, actually, Christina Koch and Jeremy Hansen completed a 41-minute manual piloting demonstration inside the spacecraft. They took manual control of the spacecraft and flew it, testing the systems, validating the spacecraft's performance. It's the kind of routine operational test that normally doesn't make headlines. But in the context of where they are right now and what's happening on the Sun, that demonstration is also a moment where the crew is actively flying the spacecraft in real time, away from automated protections, farther into space. Now let me talk about the communication delay, because this matters for understanding what happens if something goes wrong up there. At lunar distance, the speed of light communication, and that's the fastest communication possible, it's a hard physical limit. It takes 2.5 to 3.5 seconds to travel one way from the spacecraft to Earth. That means if Mission Control in Houston sends a command to the spacecraft, it takes 2.5 to 3.5 seconds to get there. If the crew responds, it takes another 2.5 to 3.5 seconds to come back. By the time Mission Control gets an answer to a question, 7 seconds have passed. 7 seconds might not sound like much, but in an emergency, 7 seconds is an eternity. 4 human beings are living right now in a machine travelling through space at 25,000 miles per hour on a trajectory toward a world that hangs in the darkness. Their daily life exists in careful routine. They eat rehydrated food that comes in packets. They sleep in shifts because the spacecraft isn't large enough for all of them to sleep at the same time. They run experiments that will determine whether humans can survive the journey to Mars. They communicate with their families through a system that sends signals at the speed of light, which means every conversation has a delay built into it. They send messages and wait for responses. Christina Koch sits in a small window of the Orion spacecraft and reads on a tablet computer, looking at images of the people and places and lives they left on Earth days ago. These 4 people are not abstractions. They're not mission statistics or flight profiles or risk assessments that get discussed in committee meetings. They're aware. They have briefings about Region 4409. They receive the HERA data that updates them on the radiation environment around their spacecraft. They can see the numbers. They understand what those numbers mean. They know what's happening on the Sun. They know what happens to human tissue when a solar particle, with the energy of an impulsive flare, passes through it. And they keep flying. They keep running their experiments. They keep eating their rehydrated food and sleeping in shifts and looking at tablets full of photographs of home. They keep doing the job they were trained to do while living with the awareness that the Sun might at any moment become lethal. That's what courage looks like when you remove the mythology from it. Not shouting or heroism or speeches, just 4 people in a small spacecraft doing the work day after day in the presence of genuine danger. Here's something that most people don't understand about space missions at this distance. The crew cannot come home early. I know that sounds counterintuitive. They're in a spacecraft. Couldn't they just turn around? But no, the orbital mechanics don't work that way. The spacecraft is committed to a trajectory. To abort that trajectory, you need fuel, and fuel is limited. To deviate from the planned trajectory and return to Earth faster would require so much fuel that you might not have enough to land safely. The minimum return time from lunar distance, barring a genuine emergency that overrides all other concerns, is approximately 4 days. After the lunar flyby on April 6th, the crew is locked into their return trajectory. The orbital dynamics are committed. There are no abort options left. They will coast back toward Earth at the speed physics permits, and they will arrive when physics says they'll arrive. And all of this happens during the escalation window for region 4409. The escalation window, the 3-day period where a 15% probability exists for the sunspot to erupt into an X-class flare, runs from April 4th at 1:17 in the morning UTC through April 7th. That's 72 hours. April 6th, the day of maximum distance and lunar flyby, falls squarely in the middle of that window. The crew will be farthest from home on the exact day when region 4409 has its highest probability of escalation. This isn't a conspiracy. This isn't hidden. This is orbital mechanics meeting solar activity probability on a calendar. It's the collision of two vastly different timescales, the rotation period of a sunspot and the orbit of a spacecraft, and they've lined up in exactly the worst possible way. NASA released a photograph a few days ago. It's a photograph taken inside the Artemis II spacecraft. It shows Christina Koch sitting in the dimly lit capsule, reading something on a tablet. Behind her you can see equipment, storage compartments, the curved walls of the spacecraft, the equipment that keeps 4 humans alive. The Orion capsule has an interior volume of about 310 cubic feet. That's smaller than most people's apartments. It's about the size of a large sport utility vehicle. 4 human beings, Christina Koch, Jeremy Hansen, Reed Wiseman, and Victor Glover, are living in that space. Right now, they are farther from Earth than any 4 humans have been in over 50 years. NASA also released a question and answer document titled Answers Your Most Pressing Artemis II Questions. That document came out on April 4th. Today, essentially. And the questions that people submitted were about safety. That tells you something important. The general public is starting to understand that something is happening up there. Questions are reaching public consciousness. People want to know if the crew is safe. They want to know what protections are in place. Let me tell you what those protections actually are, because this is where the technical details get real. The Orion spacecraft's hull is made of aluminum, augmented with polyethylene shielding. The effective shielding thickness at the critical areas where the crew is, the areas where the most sensitive organs are, is approximately 20 grams per square centimetre. That's a significant amount of radiation protection. The crew also has AstroRad vests. These are special vests lined with hydrogen-rich material that provides additional localized protection for critical organs. The spacecraft has the HERA monitoring system built in. This system detects radiation in real time and alerts the crew and mission control to radiation events. And here's the institutional framework. NASA has set a career radiation dose limit of 600 millisieverts for astronauts. For this mission, the targeting is for a cumulative effective dose of about 3% of that career limit over the entire 10-day mission. That's assuming normal solar activity. If region 4409 fires an X-class flare, that calculation changes. And here's the paradox that sits at the core of this entire situation. The crew is most vulnerable, most exposed, least protected, farthest from home, at exactly the moment when the sun is most likely to strike. They cannot come home faster. They cannot deviate from their trajectory without risking a crisis. They will be 252,000 miles away on the day when region 4409 has a 15% chance of escalation. And when they reach that distance, they will be outside the Earth's magnetic field. The magnetosphere that protects us on the ground, that deflects and channels the solar wind, that shields us from the worst of the sun's radiation, that protection ends at a distance of roughly 40 to 50,000 miles from Earth, depending on solar wind pressure. The crew will be 5 times that distance away. They will be in the open, in the interplanetary void, with only the spacecraft's hull and the shelter protocols between them and whatever the sun sends. Region 4409 is pointed directly at a spacecraft that will be 252,757 miles from Earth, with no option to turn around, no magnetic field for protection, and a shelter protocol that needs approximately 1 hour to fully deploy against an event that arrives at the speed of light in 8 minutes. That's the situation. That's what we're actually talking about here. So what actually happens if it fires? What does the decision chain look like inside mission control when that alert comes in? Part 13. What happens if it escalates? The decision chain. Let's walk through this. I'm going to walk you through the timeline second by second if region 4409 fires an X-class impulsive flare. This is not speculation. This is protocol. This is the actual decision chain that mission control has prepared for. Time 0. The flare erupts on the solar surface. Somewhere in the corona of the sun, the magnetic field lines snap. The energy releases, and X-rays, ultraviolet light, and visible light start streaming outward at the speed of light. The geostationary operational environmental satellites known as GOES are watching the sun 24 hours a day. The moment that X-ray flux spikes, the satellites detect it. We're talking seconds, not minutes. Seconds. Time plus 2 to 5 minutes. The Space Weather Prediction Center, SWPC, receives the data from GOES. The automated systems classify the flare. Is it an M-class? Is it an X-class? What's the magnitude? The center issues a preliminary alert. The alert goes out to every space agency, every power utility, every satellite operator on the planet who needs to know that something just happened. At Johnson Space Center in Houston, the Space Radiation Analysis Group, SRAG, receives the notification. Now mission control knows. Now the decision chain begins. Time plus 8 minutes and 20 seconds. This is the critical number. This is the moment that nobody wants to think about. The radiation from the flare has been travelling at the speed of light for 8 minutes and 20 seconds, and it is now arriving at the Orion capsule. X-rays, extreme ultraviolet radiation, visible light, all travelling at light speed. The radiation passes through the spacecraft's hull, it passes through the walls, it reaches the crew. The HERA instrument on the spacecraft detects an elevated particle flux. The sensors are screaming. The crew has already been exposed to the initial radiation pulse before anyone on Earth has finished issuing instructions about what to do about it. The radiation has already arrived. The deed is already done. Time plus 15 to 30 minutes. The solar energetic particles are arriving. These are the protons, the heavy ions, the subatomic shrapnel that the sun has accelerated to near relativistic speeds. The fastest ones have been travelling through space almost as fast as light. They're arriving in waves. The main proton wave is building, and the crew, if they've been properly trained and if they're following protocol, should have already begun their shelter protocol at the first HERA alert. But here's the hard part. They've already absorbed a dose from that first radiation pulse. There's no unabsorbing that. The body has already been exposed. Time plus 5 to 10 minutes after the alert, so roughly 15 to 20 minutes after the flare erupted. The crew is donning their Astrorad vests. These provide partial protection for critical organs. It's not full protection. It's localized protection, but it's better than nothing. Better is not the same as safe, but it's the direction you want to be moving in. Time plus 30 to 60 minutes after the flare, so roughly 40 to 80 minutes total from eruption. The full shelter protocol is complete. The crew has organised stowage bags, food supplies, water, equipment, everything dense enough to block radiation, and positioned them around the central module where the crew is sheltering. The shelter is holding, the flux is declining, the main radiation event is passing. The crisis, if there was a crisis, is probably over. The crew survived. But here's what happened in that window. That first 30-minute window from radiation arrival to full shelter deployment is the irreducible risk. That's the window that no protocol can close for impulsive events, because impulsive events arrive before you can react. The radiation is already there before anyone can tell you to take cover. The crew receives a dose of radiation during those 30 minutes that cannot be mitigated retroactively. That dose is absorbed. It's in the body, it's in the cells, it's done, and remember the communication delay. Mission Control's instructions to the crew are arriving by radio waves that take 2.5 to 3.5 seconds to travel there, and another 2.5 to 3.5 seconds to travel back. By the time Mission Control has confirmed what's happening, the crew has already been exposed to the initial radiation pulse. By the time Mission Control can send detailed instructions about what to do, 30 seconds have passed. By the time the crew acknowledges those instructions and confirms they're moving into shelter, another minute has gone by. The radiation doesn't wait for communication delays. The sun doesn't care about the 2.5 second time lag. Now, let's talk about what Mission Control can actually do. If Region 4409 fires an X-class flare, Mission Control has a set of options, none of them good, all of them constrained by orbital mechanics and physics. They can issue an instruction to abort the return trajectory. This would add additional days to the return journey, delaying when the crew can receive full medical evaluation and treatment. They can authorize continuation of the mission profile, which maintains whatever radiation dose risk exists through the remaining days of the mission. They can authorize an accelerated return, coming back to Earth faster if it's mechanically possible, which is limited by orbital mechanics and fuel constraints. But none of these options involve something that most people might intuitively think should be possible: coming straight home. The spacecraft is in orbit. Orbits don't work that way. You can't just point toward Earth and accelerate. You have to follow the ballistic trajectory, and the fastest trajectory home takes approximately 4 days once you're at this distance. Now let's think about the institutional challenge that NASA faces if this happens. NASA's responsibility is both to crew safety and to public transparency. But those two things can sometimes pull in different directions. If HERA detects elevated radiation, if the crew takes shelter, if they receive a significant dose during that first 30-minute window, NASA has to communicate that to the public. But the public doesn't have the context to understand what elevated radiation means. The public doesn't understand the difference between a dose that's survivable and a dose that's dangerous. The public might hear the crew received radiation exposure and interpret that as a disaster, when the reality might be much more routine. The challenge of communicating the true situation without triggering panic is a genuine institutional problem, not a conspiracy. I know what some of you are thinking right now. You're thinking, the conspiracy is that the crew is receiving more radiation than NASA is publicly reporting. And I understand that instinct. It seems plausible, but here's the counter. HERA data will be publicly released post-mission. Any deliberate underreporting would be discovered. Any astronaut involved in covering up dangerous radiation exposure would be ending their career and opening NASA to legal liability that would be genuinely catastrophic. The institutional incentive to be truthful is enormous. It's career-ending and legally catastrophic to lie. There's another angle people raise. The shelter was never tested in a real solar storm, and that's factually accurate. Artemis I was uncrewed. There were no human beings on that spacecraft. The shelter protocol has never been tested in actual solar maximum conditions. This is the first real test. But that's also true of every major spacecraft system. Right up until the moment it's used for the first time, Orion was extensively tested on the ground. The shelter was designed using decades of solar physics data. The radiation protection was engineered with the worst-case scenarios in mind. But you're right that there is an element of the unknown. There always is with something this unprecedented. That's part of what it means to go to space. You can reduce the unknown, you cannot eliminate it. Here's the callback you need to hold on to. If Region 4409 fires an X-class impulsive flare tomorrow, the crew survives. The protocols work, the shelter holds. The spacecraft is built well enough that 4 humans in a vehicle the size of a large car, 250,000 miles from Earth, can endure a solar radiation storm and come home alive. That's a genuine accomplishment of human engineering. But there is a window, 8 minutes to 30 minutes, where 4 humans are exposed unshielded to whatever the sun sends. That window cannot be closed. It can only be survived. And that is the cost of going beyond the magnetosphere. That is the price of leaving Earth's protective sphere and entering the solar wind. Everything we've covered tonight comes down to one question. Part 14. Why this matters and what comes next. How do you send humans beyond the magnetosphere during solar maximum, knowing that the margin between routine and catastrophe is 1 decimal place on a flare chart, 1 week of orbital timing, 1 solar rotation period? The answer is this. You accept the risk because the alternative, never going, is not an answer. But acceptance is not understanding. And most people don't understand how thin the margin actually is. Most people look at the 15% probability and think, well, that's pretty likely, and if it happens, we'll probably be fine. Most people don't look at the margin itself, the gap between normal and unsurvivable, the distance from M-class to X-class measured in tenths of a magnitude, the historical record that says once every few centuries the sun emits something that would be genuinely unsurvivable. Region 4409's M7.5 flare was a demonstration. It wasn't the worst thing this sunspot could do. It was a demonstration of the magnetic energy, the impulsive eruption mode, the 8-minute timeline, the operational plausibility of worst case. If you're watching this channel, you know the history. Video 5 warned the crew was flying into an overperforming solar cycle. Video 10 showed the first storms hitting them. This video is the third act. This is what happens if the sun escalates. Each tier is less likely but more consequential. An X-class flare, 15% probability, survivable with dose management. A Carrington-class event, 0.03% probability, would produce a 2-phase radiation assault that tests every system on the spacecraft. The July 2012 near-miss proved that Carrington-class events happen in the modern era. We were 1 week from a direct hit during a weaker solar cycle than the one we're in now. And a Miyake-class event, 0.0003% probability, unsurvivable in any existing spacecraft, documented at least 6 times in the tree ring record spanning 9,000 years. The cumulative probability of at least one S2 or stronger radiation storm hitting the crew during the entire 10-day mission is somewhere in the range of 5 to 10%. That's not negligible. That's not acceptable in aviation or any normal engineering context. But this isn't normal engineering, this is human spaceflight. And in human spaceflight, you accept certain margins of risk because the goal, learning how to live beyond Earth, requires you to. But here's what matters regardless of what happens. Artemis II becomes a data point. If region 4409 doesn't fire, the mission validates that the shelter protocols are robust enough for normal solar maximum conditions. If it does fire, if the crew takes shelter and absorbs radiation and survives, then the shelter protocols are refined. The radiation monitoring is improved. The impulsive flare response is optimized. Lunar Gateway, surface operations, Mars missions, everything humanity does beyond the magnetosphere will inherit this data. The mission is collecting the information we need to go farther. Artemis II is not the end of the story, it's the beginning. Every mission that follows this one will face the same radiation threat, but the risk will be worse. A Mars mission means 7 months in interplanetary space, outside the protection of Earth's magnetosphere, with no possibility of emergency return. 7 months. The statistical probability of encountering at least one major solar event during a 7-month transit to Mars doesn't sit at 5% or 10%. It approaches certainty. The physics is absolute. The data confirms it. Artemis II is the dress rehearsal for everything that comes next. Every measurement the crew collects about radiation exposure will be analysed. Every piece of data about how the spacecraft's shielding performs will be recorded. Every observation about how the human body responds to the radiation environment will be documented. That data becomes the foundation for the next generation of spacecraft. The Lunar Gateway Station will need permanent radiation shelters, probably located beneath lunar regolith or inside rock formations near the poles, places where the crew can shelter during solar particle events. Mars habitats will need more drastic protection. Mars has no magnetic field and a thin atmosphere. The regolith, the dust and rock that covers the surface, becomes the only shield available. Future Mars structures will need to be buried beneath meters of Martian soil. The physics doesn't change. The threat is constant. The only variable is how seriously we take it, and how much we're willing to invest in the protection that the physics demands. And that matters, because the tree rings say the sun can do 10 to 100 times worse than anything in our observational record. The M7.5 was 1 decimal place from X-class. The 1972 event was 4 months from Apollo. The 2012 CME was 1 week from Earth. The question is not whether these events happen. The question is whether they happen while someone is out there. Right now, at this moment, 4 humans are 169,000 miles from Earth, moving farther by the hour. The most dangerous sunspot on the disk is pointed directly at them. It has fired 4 times in the past 24 hours, and tomorrow, April 6th, they will reach their maximum distance, 252,757 miles, the farthest any human being will have travelled from home since Neil Armstrong stepped onto another world. They will be past the moon, past the halfway point, locked into a return trajectory with no abort options, no magnetosphere, no way home faster than 4 days. The sun does not wait. The sun does not care about mission timelines. The sun does not know that there are 4 human beings in a spacecraft the size of a car, farther from Earth than almost anyone will ever be. The sun has no mercy, and the margin, 1 decimal place, 1 week, 1 rotation, is thinner than anyone wants to admit. The M7.5 was a warning shot. Everybody on the ground heard it. Everybody in the spacecraft felt it. The numbers on the HERA instrument told the story in real time, and the numbers that SWPC is projecting for the next 72 hours tell the rest. 15% probability of X-class, 20% probability of significant proton storm, a sunspot group with 26 spots, 170 millionths of the solar hemisphere, a beta-gamma magnetic configuration that has already demonstrated it can produce near X-class events in confined burst with no warning, a crew at maximum distance, a shelter protocol that can't beat light speed, a solar cycle running 70% above predictions, a historical record that includes at least 6 events so powerful they would destroy everything in orbit and kill anyone caught outside Earth's protection. The margin is thin, 1 decimal place, 1 week, 1 rotation, but they're still going. And that takes a kind of courage that most of us will never fully understand. Stay with this channel, because whatever happens next, Project Nightwatch will be covering it.